All right, welcome back, everybody. Today we're going to be doing section 7.4, which is all about partial fraction decomposition. This is an interesting section, but there's a bunch of preliminary review we have to go over. So we're going to start with that. And I won't waste any more of your time. I'll just go ahead and get started. Let me pull up the slides. There we go. Okay, so there's a bit to cover, but you're going to find that there's not a lot of calculus in this section. We've got to review some definitions. We've got to review the fundamental theorem of algebra and an important corollary to that theorem. We have to review the polynomial division algorithm, if you don't remember that from pre-calculus or algebra. We need to go over an important result from the combination of these two things. Then we're going to talk about what partial fraction decomposition is, or Ph.D. And from this method comes 4 possible cases. And then only at the very end will we actually do a bit of calculus. So I know I say it later on in the slides in the lecture too, but this technique really does not have anything to do with calculus at all. It really has more to do with algebra. So most of what we're going to talk about today involves algebra. Okay, so some review of some definitions. I'm assuming that you've seen these definitions before, but if not, it's good to kind of review them. What is a polynomial? So a function p is called a polynomial if it has this structure, where it's basically a linear combination of power functions. Or in other words, you basically have a bunch of x's raised to a power, where your variable is x, and then you have coefficients for each one of those terms. That's essentially what a polynomial is. I'm assuming you're comfortable with them, so I won't spend too much time on that. What is a rational function? So a rational function is a ratio of 2 polynomials. That's pretty much all that it is. You take one polynomial and divide it by another one, you have a rational function. What is a constant polynomial? So a constant polynomial is a function of the form f of x equals c, where c is a real number. These are the functions that are just horizontal lines that cross the y-axis at y equals c. Those are constant functions. What's a linear polynomial? A linear polynomial is a function that has this structure. It's the good old line structure, right? mx plus b, the equation of a line. That's called a linear polynomial. What is a quadratic polynomial? A quadratic polynomial is one that looks like this. Oop, forgot to say p of x. P of x equals this, or f of x or something equals that. That's a quadratic polynomial. And again, a, b, and c are in R. Remember, quadratics just have to have a squared term. That's what makes them quadratic. Then going a little bit deeper into the algebra portion of it, an irreducible polynomial is a polynomial that can't be factored any further over a field like the real numbers or the complex numbers. So this is one of the reasons that you explore factoring so deeply in high school and in pre-calculus, because then you can start talking about polynomials that are irreducible or prime over some field. Okay, what is the fundamental theorem of algebra? So one thing that I always say is that if there is a theorem that is called the fundamental theorem of blank, you should know what that theorem is, and you should understand it intuitively because it's kind of the result of almost an entire field of mathematics. It's like the most fundamental results in that field. So the fundamental theorem of algebra is a very, very concise statement, but it has a lot of far-reaching consequences. So the statement is this: every non-constant single variable polynomial with complex coefficients has at least one complex root. That's the fundamental theorem of algebra. There's an important corollary that follows from that. It's this one. What it means, or what follows from that, is that every polynomial function with real coefficients can be uniquely factored into a product of powers of linear factors and or irreducible quadratic factors. All right? I want you to just ponder this for a minute, and then I'll elaborate with these next 2 bullet points. But just read this corollary a couple of times and see if you can make sense of it in your head. Okay, now let me talk about it a little bit here. So what this corollary says, what the fundamental theorem of algebra gives you is that if you've got a polynomial that's degree 3 or more, it absolutely can be factored over the real numbers, So you can factor it and your coefficients and your terms will all be real numbers. This is a critical result. And one of the things I always like to ask my pre-calc students or really any of my students, when they look at a polynomial, I just ask, can it even be factored at all? And that's a very revealing question, because if your polynomial is degree 3 or more, yes, it can be factored. That's the fundamental theorem of algebra. Yes, it can be factored. And it gets even better if you allow complex numbers. So if you have complex numbers, if you're allowed to work with the complex numbers, then the fundamental theorem of algebra gives you an even more powerful result, which says that every polynomial function with complex coefficients can be factored uniquely into a product of powers of linear factors. Linear factors. So what this means is, if you see a polynomial, yes, it can be factored. And it can be factored all the way until you get to factors that look like lines or look like parabolas. So, no matter what the polynomial is, x to the fifth plus 3x squared plus 3, can that be factored? Yes. Yes, it can be factored. The zeros of the polynomial might be gross. They might be complicated irrational numbers, but yes, it can be factored. Moreover, the corollary is saying that when you factor it, you'll end up with stuff that looks like linear factors, ax plus b, mx plus b, things like x plus 3 or 3x plus 1 or whatever, or irreducible quadratic factors, like this one, for example. This factor right here, that polynomial, that quadratic, is not factorable any further over the real numbers. It's stuck. So no matter what polynomial you have, you can continue to factor it until you get stuff that looks like this or this. The coefficients could be different, but you could still do it. This one actually might even factor some more. I mean, actually will factor a little bit more, but that's the idea. That's the idea right there. All right. If you have complex numbers, if you're allowed to use complex numbers, then you actually can factor that further. And that's what's so amazing about the complex numbers. If you allow complex numbers, then you can factor this until you end up with something that's literally like, I forget what this factors into. It'll be like x plus I, x minus I, and then because this is degree 5, you're guaranteed to have 2 more, maybe 2i and x plus 2i out of space. So the fundamental theorem of algebra gives you a very powerful result, which means, yes, you can factor polynomials. If you allow complexes, you can factor it all the way until all you've got are linear factors, which is very beautiful. Okay, here's a couple examples right here. This one is a sum of cubes. This is one of the factor forms that you should also have memorized from pre-calculus, the sum of cubes. It factors into this. And this one here, that is irreducible over the real numbers. This cannot be factored any further over the real numbers. It can be factored further over the complex numbers. And to do it, you just use the quadratic formula and find the zeros. This one right here, x to the 4th minus 2, can it be factored? Yes, it can. The degree is greater than or equal to 3. It can be factored over the real numbers, and it factors into this. There you go. That's fully factored over the real numbers. If you're allowed to use complex numbers, you could continue to factor this piece right here. Excuse me. Okay. Oh, yeah, okay. So now we're on to this. Note, this is where the dread kind of seeps in. In order to factor a polynomial, you may or will need to use the polynomial division algorithm. So we're going to review that right now briefly. But if you remember learning that in pre-calculus or in an algebra class, there's a reason that you learn it. It's because it's an important result. It's an important algorithm. And sometimes you're going to have to use it. So here it is. This is the polynomial division algorithm. Let's say P of x and Q of x are polynomial functions, and we're going to suppose that the degree of Q is greater than or equal to 0. Then there exist unique polynomial functions, f of x and r of x, such that this ratio, P of x over Q of x, can be written as f of x plus r of x over Q of x. That's what it is. Put another way, this means that you can take P of x and you can factor it. Well, you can factor it, but you might end up with a remainder depending on what the factor is. The other important point is this, and this is one thing that we're going to emphasize in just a moment here. The division algorithm says that you can take this and you can rewrite it in this form, But there's also another important detail, which is that the degree of the numerator will be less than the degree of the denominator. All right, that's a critical point, because once you get to the point where the degree of this is smaller than the degree of this, then you can't perform division anymore. You've basically fully divided it as much as you could, as much as you can. Here are the names of all those pieces. I won't dwell on them, but really this is the result that we're looking for. All right. So when the degree of the numerator is greater than the degree of the denominator in your original rational function, this theorem says you can divide, that you can perform division, and when you perform that division, you will get a structure that looks like this, where the degree of the numerator is less than the degree of the denominator. So you got to keep that in mind. This section is really all about working with rational functions and doing partial fraction decomposition. One of the things you might have to do before you can do anything else is division, because what you'll get is you'll get to a point where you'll have another rational function where the degree of the numerator will be less than the degree of the denominator. All right, so polynomial division says you can always get this. The fundamental theorem of algebra says that you can always factor this part, q of x. You can always factor it until you're left with linear or quadratic factors. You can do that. So altogether, putting both of these conclusions together, it means that if we have any rational function, we can reduce it to a polynomial plus a simpler rational function where the denominator can be completely factored. That's kind of the result. So if you've got a rational function, you can perform division and pull out that polynomial, and then you'll have another rational function, and the denominator will also be factorable. So that's the structure that we're looking for. Let's do an example here. Let's just reduce this. And by reducing it, we're going to use the division algorithm. So this is one where I want you to try it outright. So try to recall how to do long division, the polynomial division algorithm, and see if you can get the result, and we'll do it together in just a moment. All right, now let's do it together. The degree of the numerator is greater than the degree of the denominator, so we can perform polynomial division. And when we do, this is what your result should look like. Yours should look similar to this. Whatever technique you use for this is totally fine. This is just one way that I learned how to do it, and one of the ways that I teach how to do it in my classes, so here we go. What we just did was we took this, we took this and we rewrote it as this polynomial plus this remainder divided by this divisor. That's essentially what polynomial division does, and I have that written right down here. So we took this rational function, and we were able to use division to rewrite it as a polynomial plus this new rational function. The denominator will still be the same, but the numerator is different. Moreover, the numerator has a degree that is less than the degree of the denominator. So we can't divide it anymore. And then once again, the fundamental theorem of algebra says these types of expressions, these quadratics, or those types of polynomials, could be factored. In this case, it can be factored even further, like so, unless this is irreducible. If this is irreducible, then it can't, irreducible over the reals, then it can't be factored again. But this one actually is not irreducible. You can factor it again, and you get x minus 3, x minus 4. So, long story short here, we can turn something that looks like this into something that looks like this, and this is much easier to integrate. That's the idea. Okay, now we're here. Let's talk about what partial fraction decomposition really is. So like I mentioned at the beginning, this really has nothing to do with calculus. This has nothing to do with calculus whatsoever. It's a purely algebraic technique, and sometimes it's actually taught in a pre-calculus class or in a college algebra course. I know that at UCR, they actually teach partial fraction decomposition in pre-calculus because it has nothing to do with calculus at all. It's an algebraic technique. So I actually kind of preferred that because the technique is, it can feel very cumbersome until you get comfortable with it, right? So there's already so many things you have to get comfortable with in Calc 2 that I kind of like the idea of moving this concept back into pre-calculus. But then there's also a ton of stuff you have to cover in pre-calculus already, so it becomes kind of a thing that gets pushed around. Where do you do it? Where do you not do it? We're going to do it here. All right, so nothing to do with calculus. Why do we use it in calculus? Because in calculus, we use it to make integrating rational functions easier. That's always the goal with these integration techniques. We want to make the integral easier to evaluate so that we can evaluate it. So what I'm going to do here is I'm going to emphasize the algebraic process first, and then we're just going to use calculus at the very, very end of the lecture. We're going to do a bunch of examples where we perform partial fraction decomposition on a rational function. And then at the very end, we're going to be like, oh, now we can integrate these things. Boom, boom, boom. All right, so here we go. Remember how way back when you learned how to work with fractions, even the first time you started using fractions back in elementary school, when you would combine sums and differences of fractions, you would find a common denominator, you'd find an LCD. You would multiply each term of the sum or difference by 1, and then you would write the result as a single fraction. So, let me do an example. If you had to do 1/3 plus 1/2, you would be like, oh, the least common denominator is 6. And so you would multiply 3 or 1/3 by 2/2, and you'd multiply 1/2 by 3/3. And then from that, you would get 2/6 plus 3/6, which is 5/6, right? You remember that process, right? So if you remember that process, partial fraction decomposition is the opposite. It's literally the opposite of that process. It's saying, what if you started with this? How could you go backward to get to something that looks like 1/3 plus 1/2? That's really what it is. And the process can be a little bit tedious, mainly because there's 4 cases that are involved. So we're going to go through all 4 cases now. But let's start with a rational function. Let's say we have a rational function p of x over q of x that's been fully reduced. So we've already performed the division algorithm if we need to. The degree of the numerator is less than the degree of the denominator. Then partial fraction decomposition involves rewriting this fraction as a sum of partial fractions that are of this form. Either this or this. And we're going to basically add up a whole bunch of things. So we're going to take this thing and we're going to convert it into stuff that looks like this plus stuff that looks like this. That's the goal. Now, the fundamental theorem of algebra, or that corollary, guarantees that we're going to have 4 possible cases after possibly using the division algorithm. So that's one thing I want to remind you is if the degree of the numerator is greater than or equal to the degree of the denominator, you need to do division first. Do the division algorithm first. Then once you have a fraction that's fully reduced, you're going to end up with one of these 4 cases, or I'm sorry, just some of these 4 cases, and we'll go through them right now. The denominator could be a product of distinct linear factors. It could be a product of linear factors, but some of them are repeated. The denominator could contain some irreducible quadratic factors, none of which are repeated. Or the denominator could contain irreducible quadratic factors, some of which are repeated. All right, so these are the 4 cases, and it's the fundamental theorem of algebra that guarantees we're only going to have these 4 cases. Because again, our denominator, q of x, this little guy right here, q of x, if it's a polynomial, it can be factored. That's the fundamental theorem of algebra. And moreover, it can be factored until you're left with linear factors and or irreducible quadratic factors, no matter what. And that's where these 4 cases come from. Linear factors only that are not repeated, linear factors only, some of which are repeated. Maybe you have some irreducible quadratic factors, but they're not repeated. Or maybe you have some irreducible quadratic factors and they are repeated. Those are the 4 cases. And how you deal with them is, it's kind of, you'll see, it's kind of the same thing. Once you get the first couple, you can get all the rest. All right. In this case, so we're doing case number 1. So case number 1 means that our denominator q of x can be factored into distinct linear factors. Remember, linear factors are factors that have the structure of a line, like mx plus b. So if you have this situation, kind of like we do down here, then we're going to rewrite our rational function as a sum of fractions of this form. These are the partial fractions. So there's some coefficient over some linear factor, some coefficient over the other linear factor, dot, 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 some coefficient over the last linear factor. So this depends on how many of these factors you have, and that depends on the degree of Q and some other things, since we're working over the real numbers and not the complexes. But if Q of X is a product of distinct linear factors, then it will be able to be decomposed into a structure that looks like this. And at that point, the goal is to find what all of these coefficients are. That's what we're going to do. So here's an example. Let's start with this rational function. Notice the degree of the numerator is already less than the degree of the denominator, so we do not need to perform division. We can just move forward. The denominator factors into a product of distinct linear factors. So what that means is we can write it like so. We can write this rational function as some number a divided by x minus 3 plus some number b divided by x minus 4. And we need to solve for a and b. That's the goal. So I'm going to show you how to do this in two different ways. The first way is going to be like the universal way. This is the way that will always work. And the second way is going to be kind of a shortcut. So here we go. Starting with this equation, multiply both sides by the LCD, and you get this equation. Now what we're going to do is we're going to basically expand everything. So expand this, and you get this result over here. Now we're going to combine like terms and then factor out the common factors. So ax and bx are like terms, so we can factor a and b out. We can factor x out, and we get a plus b times x. Negative 4a and negative 3b, those are the constant terms, so we're just going to group them over here. All right, now we've got everything kind of massaged in just the right structure, and now we can compare coefficients. So we're going to compare coefficients, and this is kind of a fun thing to do, I think. Because we know that 3x minus 10 has to be equal to this, we can just directly compare the coefficients of the linear term and the constant term. So notice this side says 3x, this side says a plus bx. That means that a plus b has to be equal to 3. And then this side says negative 10, and this side says negative 4a minus 3b. That means that these two things have to be equal. So we get two separate equations in two unknowns, and then we get a system of equations. So a plus b equals 3, negative 4a minus negative 3b equals negative 10. And then when you solve that system of equations, you'll find that a equals 1 or b and b equals 2. Thus, a equals 1, b equals 2, and we can rewrite our original rational function as this sum of partial fractions. And this is much easier to integrate. That's much easier to integrate. Hard to integrate, easy to integrate. And that's the goal. Okay. Now I'm sure some of you were probably groaning at home when I said solve this system of equations, because if you remember how to do it, it can be kind of tedious, right? You can use substitution or you can use elimination. It can be kind of tedious. It does always work though. As long as you've got two equations and two variables, you'll be able to solve it. And that's an idea that gets generalized in linear algebra, so it's good to make sense of it now. But there is an easier way to do this. So this method works, I'll say all the time, but sometimes you have to do more than you might want to do to get it to work this way. So sometimes comparing coefficients is just the easier way to go. Two different techniques, right? Okay, so that method will always work, and it's very good for a computer because a computer is really great at solving systems of linear equations. That's a lot of what linear algebra is about, is learning how to solve systems of linear equations in an algorithmic way. But sometimes there's a simpler way to find these coefficients. And we're going to go back to this equation that we had after like step 2, or this is step 2. We're going to be clever. We're going to choose x equals 4 and plug it in for these values, the values of x. Then we get this equals this, which means b equals 2. Then we're going to let x equal 3. And when we plug x equals 3 into these, we get this, which means a equals 1. And those are our coefficients. That's the trick. So basically, look at these linear factors you've got and basically pick the opposite of this and plug that in for x. and that'll eliminate one of the variables. The reason that that works is because when you plug in x equals 4 here, this entire term disappears, and then you're just left with one unknown. And when you plug in x equals 3 for here, this entire term disappears, and you're left with one unknown. That's why that's working. So you can do that. It's very quick, it's very easy, it's very satisfying, and you get the same result. There you go. Okay, now we need to go to step 2, or I'm sorry, case 2. So case 2 is where the denominator is a product of linear factors, but some of them are repeated. Some of them are repeated. So for example, here's one right here. And rather than show you the general form, I'm just going to use this example to explain the structure of the technique. So here we've got a denominator where the factors are linear, but they're repeated factors. So this one has multiplicity 2, this one has multiplicity 3. So what that means is that we can decompose this fraction into a sum of fractions that look like this. So a over x minus 2, b over x minus 2 squared, c over x plus 7, d over x plus 7 squared, and e over x plus 7 cubed. So what's happening here is you need to include a partial fraction for every subpower of every factor. So now is a good time to groan because you can probably see that this would take a long time if the multiplicity of these factors is large, right? And you're going to get a very large system of equations, even with a very simple rational function. But look, see the degree here, or the multiplicity here, is 2. So that means we need a partial fraction when the degree is 1, or multiplicity is 1, and we need another one for when the multiplicity is 2. This factor has multiplicity 3, so we need a fraction for each one of those powers. Multiplicity 1, multiplicity 2, multiplicity 3. And that's it. So if you've got repeated factors that are linear, this is the type of structure you're going to have to use. All right? Let's do an example. This is one I want you to try on your own first, and then we'll do it together. So think about it first. Try to write what, or at least think about and say what you think the decomposition will look like. All right, now try to write out what the decomposition is. Okay, let's do it together now. Let's see, we have linear factors, but this one is repeated. This one has multiplicity 2, so we're going to need 2 partial fractions for that particular factor. And this is what we get. So this thing, we know that we will be able to decompose it so that it's written like this, plus this, plus this. All right? Now everything is the same. So realistically, at this point, the techniques are all the same, and we've already done both of the techniques you would use. You have the decomposition, you now just need to find those 3 unknown coefficients. How do you find those 3 unknown coefficients? You need to get an equation, or I'm sorry, you need to get 3 equations in 3 variables. Once you have 3 equations in 3 variables, you can solve for those unknowns, and then that's it. That's all she wrote. But we can use that trick that I explained, and maybe that'll shorten things a little bit, and you won't have to just do coefficient comparison. So first step, multiply everything by the LCD, and you'll get this equation instead. So notice here we had a over x minus 1, and now we're going to get a times x minus 1 times x plus 2, because that's what's missing from the denominator here. We're going to get b times x plus 2, and c times x minus 1 squared. Now you just make clever choices of x to eliminate some of these terms, and then you'll be able to solve for the remaining one. So here we go. Let's let x equal 1. So when x equals 1, this term disappears and this term disappears, and all you're left with is this term. So we get that 1 squared plus 2 equals 3b, so b is equal to 1. Check, we got 1. Next, let x equal negative 2. When you let x equal negative 2, this whole term will disappear, this whole term will disappear, and then you're just left with this one and then this. So you'll get 4 plus 2 equals 9c, so c equals 2/3, boom, there's 2. Now what we have to do is take the results that we just got and substitute those in. So substitute those in for b. So like turn this b into a 1 and turn this c into a 2/3. And then you can pick any other value you want for x. Any other value you want for x. Notice here there's no other suggested value. We chose x equals 1. We chose x equals -2. And we already got as much as we could from that cleverness. Now just pick any other value of x that's going to make your life easy, like maybe x equals 0, and you'll be able to solve for the remaining unknown coefficient, a, after you substitute b and c. So once we substitute b and c right there, we're only left with the unknown a. We plug in x equals 0 and ... we get a equals 1/3. Hooray! Now we can finalize our result. This fraction here, this rational function, is equal to this. And this is much easier to integrate. Much easier to integrate. Another side note, yes, you should just leave these coefficients as fractions in the numerator. I find that to always be easiest because when we actually do the integration, you're going to be able to just pull these things out of the integral anyway. So rather than kind of like merge it, you might as well just leave it in there, leave it at the top. That's case 2. All right, what's case 3? So case 3 is when your denominator contains irreducible quadratic factors, none of which are repeated. So here are 3 examples of irreducible quadratic polynomials. So x squared plus 1 is not factorable over the real numbers. It is factorable over the complex numbers though, and that's why complex numbers are nice. But we're not working with complex numbers in this class, sadly. You'll have to save that for another class. Maybe I'll get to teach it to you someday, but not right now, sorry. This is irreducible, this is irreducible, this is irreducible. And so what that means is if we have these appearing as factors in our denominator, like down here, then we're going to have to include a partial fraction that has a linear numerator, a numerator of the form ax plus b. So let's try it. This is a simple example, x minus 1 times x squared plus 1. X squared plus 1 can't be factored any further over the reals. And so here's what the decomposition looks like. That's the idea. This is a good time to point out that really it's the fundamental theorem of algebra that's giving us these results, because if this thing is irreducible, how do I put it? Well, okay, I'll say it like this. Notice that like here, the degree of the denominator is 1, but the degree of the numerator is 0. It's a constant term, right? Constant terms are degree 0, linear terms are degree 1, quadratic terms are degree 2, right? So it's literally 0 over 1 versus 1 over 2. That's what it is. So anytime you have an irreducible quadratic factor that pops up, you're going to end up with a partial fraction that has a linear numerator because the degree is 1 less. The degree is 1 less. And then after that, everything is the same. Everything is the same. The techniques are the same. The process is the same. The only catch is that this is the structure now. One note I'll make too, and if you want to ask about it later, you can. Sometimes these coefficients will be 0. That's usually a question people want to ask, which is, hey, when I go through this process, is it at all possible that A, B, or C is 0? And the answer is yes. You might end up with a 0 for those coefficients. They could be any real number. It really just depends on what the denominator, what the function is, what the polynomial is. All right, so starting here, we're going to multiply both sides by the LCD, and then we get this. All right, now we can choose some simple, or sorry, choose some arbitrary but simple values for x, and that'll let us solve for the coefficients. I'm not going to go through the process again, but I will say this. Why don't you try to do this one right now? Oop, let me hide it. Pretend you didn't see that. Pretend you didn't see that. Start with this. Plug in some simple but helpful values of x and try to find what A, B, and C are. Go for it. All right, now let's do it together, or let's at least see the answer. So when you do that, you'll find that A is 1/2, B is -1/2, and C is also -1/2. And that's the decomposition. And this is easier to integrate. That's it. All right, almost there. One more case, case number 4. And you can probably guess what this case is going to boil down to. This is when your denominator contains irreducible quadratic factors, but some of them are repeated. Some of them are repeated. And as you might guess, all you're going to have to do is you're going to have to include another partial fraction with a linear numerator for every subpower of every irreducible quadratic factor in the denominator. There it goes. All right. So, for example, this one has a repeated linear factor and it has a repeated quadratic factor. So we're going to end up with a bunch of partial fractions, some that will have a linear numerator. Here we go. This decomposes into something that looks like this. We've got this fraction for one of these powers. We've got this fraction for the other power. We've got this fraction for one of these powers. And we've got this fraction for the other one. And that's basically the idea. That's basically the idea. I'm not going to go through this example, but hopefully now you can see that this can very, very quickly become a difficult problem to solve. And this is why we like computers, and this is why we study linear algebra, and this is why we teach computers to do linear algebra, because solving a system of equations like this in 5 or in 6 variables is something a computer can do very, very quickly and very, very easily. So what is the human component to all of this? The human component is knowing the fundamental theorem of algebra, knowing that if I've got a polynomial that it can be factored until I end up with linear factors or quadratic factors. That's what the humans need to know. Once we know how to factorize it, we can then have a computer solve for all the coefficients of the partial fraction decomposition. That's a mouthful, but that's it. All right, now, almost done, but guess what we get to do now? Some calculus. So we have not talked about calculus at all this entire lecture. It's already been going on for 37 minutes. Haven't talked about calculus at all. Maybe mentioned integration a little bit, but here's how we use it in calculus. Let's say we want to compute this integral. Well, this is ripe for partial fraction decomposition because it's a rational function. It's already, the degree of the numerator is already less than the degree of the denominator, so we don't need to perform the division algorithm at all. We can just factor the denominator, or I should say, the denominator either factors once more, or it's irreducible quadratic. If it's irreducible quadratic, then you're basically done, and what you'll have to do, hint for the activity, is you'll have to complete the square. We'll talk about that later, though. All right, here we go. Earlier in the lecture, we already decomposed this into this. So now we need to integrate this function, and this is very easy to integrate. We can split it into 2 integrals, and then we can just use the natural log function. There we go. Boom. So decompose this into partial fractions, and then you get something that's simple to evaluate, simple to anti-differentiate, and there you go. Boom. All right. How about this one? Evaluate this. So this one, we found the decomposition. We found that this fraction decomposes into these 3 partial fractions. Now we can split this integral into 3 separate integrals. This one I went ahead and evaluated. This one I left unevaluated for 1 step. And then this one I already evaluated. Notice we don't have a plus c yet because there's still an integral involved, so we don't need a plus c just yet. How do we evaluate this integral? We're just going to do basic u substitution. Let u equal x minus 1. You get 1 over u squared. Anti-differentiate using the power rule, and then substitute back in, and there you go. So this thing, the integral of that is this, which is pretty cool. Pretty cool stuff. There's also there are some intimate connections between why we have these factors and why the natural log is coming into play. But maybe I can talk about that when you'll have some free time. Okay, now there's this one. So this one's got an irreducible quadratic factor in it. It's got a linear factor in it. We found that the decomposition was this after partial fraction decomposition, and now we end up with 2 easier to evaluate integrals. So I'm going to do this 1 step at a time. This integral right here is easy to anti-differentiate, or is easy to evaluate using log, because that's the antiderivative. You could do a U substitution, and this is the same thing you would get, but I want to point out another helpful technique here. So sometimes if you have a fraction like this that isn't yielding itself well to a substitution, it's helpful to split it up and write it as two separate fractions, right? So we can write x plus 1 over x squared plus 1 as x over x squared plus 1 plus 1 over x squared plus 1. And now we have two integrals to evaluate that are easier to do. So this one we can tackle by using u substitution. Let u be x squared plus 1. Then when we differentiate, that's where we're going to get our x dx, right? And then this one, this one is arctangent, right? that's the derivative of arctangent. So we can just go straight using that result. This one, u substitution, evaluate that integral using the power rule, substitute back in, and then boom, you're done. All right. So I know it's a lot of stuff, but again, not really much calculus. The calculus is pretty minimal. The calculus techniques that we're using are techniques that you already know from previous sections. All we learned in this section was a new algebraic technique. And on that note, let's play. So I'm excited to do this activity with you because it's a good review of algebra. So if you haven't used the division algorithm for a while, or if you haven't factored for a while, this is a good review of all that stuff. So I'm excited to do this activity with you. All right, on that note, I will say goodbye. Thank you again for listening, and I'll see you next time.